Now, in order to implement our sampling algorithm, it's going to use this divide and conquer strategy, very similar to what we did when we were generating samples from the auto-logistic model in the previous chapters. And in order to do this computation, in order to do this sampling through Gibbs sampling, we need the full conditionals of each pixel in the true image, right? So each pixel of that. So the full conditional of xi. And so what I want you to do now is to just take a few minutes and see if you can derive the full conditional of xi from this expression here. So pause the video now and have a go at that. Alright, welcome back. Well, this is one that I prepared earlier. We need to keep everything that's going to depend on the term xi. And if we look up here at the conditional of y given x, well, xi is only going to appear in the product, so the ith term of this product, right? The term that corresponds to the pixel we're looking at, right? So we pick up a 1 minus theta zi, 1 minus theta zi, and then if from the auto logistic part we just pull out the bits that involve an xi. We can simplify this a little bit further, so we can bring everything up into the argument of the exp. So we can write this as zi log 1 minus theta plus 1 minus zi log theta plus alpha xi plus beta xi sum j such that j is a neighbor of I of xj. And we can then simplify that a little bit further, right? So we see that there's a term here, there's a log theta term, which doesn't involve any zi. It's certainly not going to involve an xi, so we can just get rid of that, and we can say that that's proportional to, so zi, so we'd say minus zi log theta over 1 minus theta. So we pull out the minus here to give us a log, something that looks like the log odds, plus alpha xi plus beta xi, the sum j such that j is a neighbor of I of xj. Alright, and now what we'll do is we'll plug in what zi means. So just to remind ourselves, so zi is xi yi plus 1 minus xi 1 minus yi. Well, we know that we want to isolate the xi's on their own, so it makes sense to maybe expand this. And if we do that, what we'll get is we get xi yi plus 1 minus xi minus yi plus xi yi. So that will give us 1 minus xi minus yi plus 2 xi yi. So plugging that in here, we get this expression, and then what we can do is we want to isolate the x on its own, right? So we're going to have something which is a probability mass function in x, and we pull out everything just that includes x. So what that leaves us with is okay, we have an xi, we'll have alpha plus, what are we left with here? We'll get a 1 minus 2 yi log theta over 1 minus theta, and then we have the bit for the neighbors then. All right, that's our full conditional then for x. So this is a probability mass function in x. X can take values either 0 or 1. What we do is by conditioning on the neighbours around x, the neighbouring pixels, we can compute the probability mass function for x. And the main difference with the Gibbs sampler that we implemented previously is that we now have the incorporation of the noisy image, and that enters here. Right, so it's like an extra term that we have for the pixel observation. Of course, it involves theta, which describes the noise generating mechanism, and the actual observation of the noisy image at pixel I. And then with this expression, well, this is what we need to implement our Gibbs sampler. So what we can do is begin by initializing the true image. Then we sample from the full conditionals. For many sweeps. And the result is that we get a kind of a collective sample of what the true image is. Now this all makes kind of more sense when we try and implement it practically. And that's what we're going to do in the next video. So whenever you're ready, head over there.